Okay, so this is the environment that we described: Azure Cloud, Edge Server, Equinix Fabric in the middle, Git with information here, and Emco deployed with CDS. Right. So the next thing we're gonna discuss is what's in the GitHub. Right. So we have the cluster config. So GitHub is shown here. These are the CDS CBA repositories. So this is the actual blueprints that are running the API execution. So the API executor, the Helm chart processor, and the Terraform plan executor, they're all stored in Git, but these are already integrated into the Mco 2.0 deployment. So the cluster config file you see there is just stored in Git. We just did it for the demo to pull it down from the repo based on the API call. Then we have the Helm charts for the application. They consist of 3 parts. Then the Terraform plans are also stored in Git, and this is specifically for using Equinix and Azure Terraform providers. And the contents here is basically Terraform syntax. It creates the layer 2 connection, creates BGP, creates peering. All the addressing that you see here are all real, and completes that across Azure and Equinix. So next time we'll look at the Mco deployment. This is based on Aarna Networks Mco 2.0. So this is deployed in the just on a server in the lab. And right now you see the tenant is defined, but there is no services or service instances. It's basically an empty shell, no clusters defined here. So the next step, we will look at basically what pods are running as part of that Mco deployment. So we'll see ONAP components here, Mco UI that is shown right here, and the CDS with pre-integrated blueprints already. So next thing we'll look at the actual CDS structure, or the blueprint structure that we implemented. So this is just for convenience, so we can clone that to show. So there is a API executor, chart processor, Helm chart processor, and the Terraform plan executor, right? And there are templates that are populated based on the real credentials and parameters during the API call, but they look like this. So this is, for example, a template for the Terraform that includes access credentials to Azure, GitHub, and some parameters. So the next thing we'll execute a REST call to register a edge cluster to the Mco registry, right? Using the REST call. It'll pull down the cluster config, and it'll automatically register that into the Mco cluster repository. So for that, we execute the script. The script is basically an API call, but the payload we're not showing here because there is sensitive information in there. It's in the file that's stored locally, the payload itself. The file the call just executed, and we'll look at Mco, and we see the cluster just appeared in the repository on the orchestrator. And that's the cluster that was in the picture on the left. So the next step we'll do is look at, so this is the cluster that is provisioned in the lab. The next thing we'll do is make a call to actually execute the Terraform plan. That Terraform executor will pull the plan from the Git repo, create infrastructure in Azure Cloud, and create the virtual connection, which is basically, in the Metro Ethernet forum terms, is the EVC inside the interconnection fabric. So again, we're executing the REST call using this script. So it just kicked off the Terraform plan, and we'll see some of the output from the log for Terraform executor in a second. So it's running, and basically it goes through what you would see when you do Terraform init and Terraform apply. So all of these parameters will be created. And now we'll look at the Azure Cloud. At this time, so this is Azure portal, and at this time I'm looking at the express route circuits, and there's nothing there yet. So refresh the view, and we see the express route circuit has been created, and it's now in an invalid state, pending provisioning on the interconnect provider, which is Equinix. So we're going to go look at, so you see it's disabled, and we're going to go look at the Equinix customer portal to see if that connection is there. So you'll see at the bottom there, PCI test, VLAN 543. So that's the connection that has been created automatically inside the provider, and that's the layout. Azure requires a redundant connectivity. So let's go back to Azure portal and see what's going on there. So at this point, it's still not provisioned, but we see the Bgp Peering configuration started. So this was created by Terraform. So at this point, it's still not provisioned fully. So we go back and just take a look at the status, what's going on the interconnect provider side, and it's provisioned, but it's pending the completion of BGP. Those are specifics of how Azure Cloud requires direct interconnect. So the same is possible with AWS, for example, with direct connect. So after refreshing, we'll now see that the circuit has been fully provisioned in Azure. That means the interconnect has been provisioned as well. And now we'll look at the, yes, and the BGP peering is configured, but it's not up, right? So at this point, we're going to make a call, REST call to deploy the actual application. We'll pull down the Helm charts. There are three charts for CRD, the actual IoT edge for the pods that you see there, Cube router for BGP. And then once this is done, the BGP connection is supposed to come up, and we should see end-to-end connectivity. So at this point, inside the orchestrator, there is no service. There is no service instance. So we're just going to execute the script with the REST call so that all of that is onboarded. So, yep, so the script has been run here, and it completed successfully, and it created this service, PCI Azure IoT Service CDS. And we'll go to the orchestrator and see under the tenant Equinix, we see that service created. And there are three applications. It's a composite application, but there's three components: Cube router, CRD, and the actual charts for the Azure IoT application. So just look at the edge cluster to see, just to show that there's nothing running except for the system pods. So we're going to create here a service instance. This could be done with an application call, but this is, we just chose to do it manually here. So create a service instance based on that service that was pulled down from Helm charts. These are the three components. We map those components to the edge cluster that was created also in the previous step. And we submit that and deploy. It's successfully deployed. So at this point, we'll look back at the edge cluster, and you'll see up on the top we have the cube router daemon set deployed, and we have the application pods starting to come up. And at this point, the four application pods are up in the default namespace. And that means that the CRD has been deployed, because otherwise they wouldn't come up. So we will also look at the services. So the one pod that is listening to the IoT messages is exposing port 50,005. So now we'll check the status of the BGP connection on starting with Azure. So here is the Bgp Private Peering. We'll look at the route table summary. Yeah, we see the peer that came up, and note the IP address, which is correct, and the 10 prefixes it received, which are basically pod siders directly. So there is no load balancer IP. we did it so that there is direct access to pod IPs, between cloud and the edge, and these are the prefixes that are advertised from the pod or from the pods running on the edge cluster. So we're taking a look inside the kube router container. And at this point, we see BGP, this is written in Go BGP. This is Go BGP, and these are the prefixes that it's advertising. The neighbor status here is also established, right? So this is the neighbor that we're talking to on the Azure side, and it's saying it's established. And we'll just check connectivity by pinging and setting up a TCP connection to the exposed port by the application pod. So here's the pod IP that is and the port that has been exposed, right, by the application, and we'll ping from that into the test VM that's on the Azure side in the private VNet across that private interconnect from the pod IP that has been used by the IoT pod that's called LoRa read. So we see pinging, but also notice the latency. It's less than 3 millisecond round trip time. That's between the edge server inside the Equinix data center and Azure region in US West. And we do the reverse. So this is right now on the test VM on the other side. So this is the test VM on the Azure side, and we'll just basically ping back just to show that it's bidirectional. And we'll open a TCP connection to that pod IP on the exposed port just to show that the TCP traffic is passed. And at this point, we will now show the simulated IoT client sending encoded messages into the edge, and edge processing and decoding that and sending into the cloud. So to do that, we have this code that is simulating the client, and we're gonna basically send it to the from the access side, from the access network to the exposed pod IP on the exposed port again. So this is happening on the network side, so it could be happening behind the wireless UPF. In this case, it's just the access network, and you'll see here that the messages are encoded, and we'll look at the logs on the edge side. So again, if you look at these messages that are sent, they have sequence numbers. This is number 4, and then have the encoded payload, which is really temperature, pressure, and humidity readings, but they're encoded in low power format. And on the log in the pod, we see them being decoded and sequence numbers incrementing. And also on the cloud side, this is all posted to the cloud. And then if we look at the IoT service, we see this edge device shadow that is defined. That's basically deployed as pods on the edge. But here those are shadowed in the cloud, their status and their software, their authentication and other parameters. And then if we look at the statistics for that IoT service, we'll see the messages that are coming in that have been decoded. We'll just look at the aggregate number of messages received. Right, if we look at that, then we'll see the graph that's basically showing that the cloud is seeing those messages. So that's really the demonstration for this session.